This is chapter 8, devoted to applicative functors and profunctors. The first part will be practical examples. The main motivation for applicative functors comes from considering monadic computations, or computations in the functor block, as I call them, in case when effects are independent and commutative, or in case when these effects could be executed in parallel while the result is still correct. Here's an example. Consider a portion of a functor block or a four-yield block in Scala that looks like this. There are three future values, and x will be waiting until this future value is ready. Imagine that these are some long-running computations. And after these three lines, we can use x, y, z in further computations, and any further computations will be waiting for these three futures. Now, if we write code like this, then these three futures will be created sequentially. That is, first, this future will be created and scheduled on some thread, and then when it's done, you get the value x, and then the second future will be created and scheduled, even though it doesn't use the value x, but the monadic block, or the four-yield block, or the functor block, whatever you want to call it. I call it a functor block. The functor block is such that every generator line blocks everything else until it's done. So in the future will be created one at a time, and so obviously this is not optimal. If you translate this into Flatmap code and map, that's the code. So you have the first future to which you append this Flatmap, so you schedule this further computation only when the first computation is ready. The second future will be then started, and this will be waiting until the second future is ready, and then the third future will be started, and this will be waiting until the third future is ready. Clearly, this is not optimal. We'd like to parallelize these things, and we have seen in a previous tutorial that a very easy way of parallelizing such computations is to create the futures before starting the functor block. But this is actually a specific feature of Scala, where futures already start computing when you create them. There's no separate method to start computing them, which is actually a design flaw. And we would like to express more carefully that certain computations can be done in parallel because they're independent, whereas other computations really have to wait one for another. Now, in this example, like I said, C1, C2, and C3 are just some fixed computations that don't depend on the values computed previously. If we do have this dependency, then of course there's no way except to wait until each previous computation is done. But in case they're independent, we would like to be able to compute them in parallel. And we would like to express that in a better way in code, rather than just a hacky way where you create these futures separately and then put into some variables, and then you write this code. Because that will work for future, it will not work for some other functor. Another use case where monads or monadic effects are not exactly what we want is a case when we perform computations that may give errors. Now, we have seen in the previous chapter that using a monad, such as either monad or option monad, we could stop at the first error very easily. But sometimes we don't want to stop at the first error. We want to maybe accumulate all errors as much as possible and then give the user more information. So monads cannot do that in general. They cannot accumulate all errors, because if one monadic step fails, then the next one won't be executed. So if, as I said, effects are independent, then we would like to have a different way of computing than the monad computation shown here. So monads are inconvenient for expressing independent effects. Also, they're inconvenient for expressing commutative effects, because typically when you change the order of generator lines, like these two, you change the results. Even though these generator lines seem to be independent of each other, they aren't. The computation will first iterate with x going over this list, and for each x, y will be going through that list. In that order, first x will be iterated over this list, then y over that list. That order is fixed, and you can do nothing to change it. So, for example, if you interchange these two lines, you would get a different list as a result. You have the first iteration would be interchanged with the second one, and the list will have a different value. Now, for lists, the order of elements is important, perhaps. For other monads, usually this is also the case, that you cannot just interchange lines in a functor block and expect the result not to change. However, there are some cases where these computations, logically speaking, are independent. And what we would like to do is express this very clearly. This is how it is done. We would like to have a function that computes something like this, but assuming that the effects are commutative. How would that function work? Well, look at what it does. We have here two containers, and we compute some function from values that are stored in these two containers, and we put all the results in a new container. So if we just express this computation as a function, that function would have the following type signature. It will take two containers, let's call them FA and FB. So let's say F is list, and A and B are going to be the types of the elements in these two containers. In this example, both integers, but in general we might have two different types, A and B. So this function takes these two containers. It also takes a function f, which is a function from a pair AB to some type C. As a result, we get a container of type C. Now clearly, this kind of function, let's call this map2, because it's like map, except you have two containers and two arguments of a function that you use. Now, of course, this computation has this type signature. So if you have a monad for f, then you can define this function using this code very easily. X left arrow fa, y f arrow left arrow fb, yield f of xy. So that is the code that implements map2 in terms of Flatmap and map. Now, the key observation here is that we would like to not use the Flatmap, because Flatmap will force this ordering of effects, and it will prevent us from having commutative effects. Whereas this function we could define differently. We could define it separately from Flatmap in a different way, such that this function is symmetric in A and B, for example. We could do that. Once we are able to do that, we can use that function by itself without writing functor blocks, maybe using a different syntax, but basically just using this function to prepare this data in this way. So to process several containers in a symmetric way, that is, two or more independent containers having independent effects, and a function that maps their values to some new type, and the result is a new container. So that is the key idea behind applicative functors. Applicative functors are functors f for which this function is available somehow. Also, the function pure, the same function as in monads, with the type signature a going to f of a, must be available. But that function, just like in the case of monads, is much less important for practical coding than this function. So applicative functor is a functor that has these, but first of all, it does not have to be a monad. And even if it is a monad in some way, the definition of map2 does not have to come from the definition of Flatmap like this. So the reason is that we want a different logic. We don't want the calculation going like this with flat maps. We actually want to avoid using flat map. So that's why we would define map2 separately, not via flat map, and use that function map2 directly on some containers. In this way, for example, we would be able to define a function of 3 futures that takes also a function of 3 numbers and computes a future of the result. Now that would be map3, as it were. So let's consider this as a generalization. So as I said, for a monad we can define these functions through Flatmap, and let's just use that as a guide. We're not going to define it through Flatmap really, but we should be able to get a lot of intuition by just looking at the functions that we get from Flatmap, because the types are going to be the same, and so a lot of intuition comes from looking at the type of a function. So if we just have one container, then it's an ordinary map, which is equivalent to this code in Scala. I remind you that the left arrow, or the generator arrow, is translated into either flat map or map. If there are several generator arrows, it's the first until the last one, so the last but one, all of them are flat maps, and the last one is map. So the last left arrow before yield is just translated into a map. So that's a map. Now this would be first a flat map, then an ordinary map, but we want to replace that with this kind of syntax, perhaps, where we have map2 that takes a tuple of containers. It also takes a function f with 2 arguments, and it returns a container. Here is a similar thing with 3 containers, where we have map3. So the function f needs to have 3 arguments, and the result is again a single container. So how do we generalize this? let's write down the type signatures. So map, the usual map, let's call it map1, just to be systematic. Then it's like this. This is the standard type signature for the map function. Map2 has this type signature. It takes two containers, as we already saw on the previous slide. Map3 takes three containers. It takes a function with three arguments instead of two, and it again returns a new container. So clearly this is how we can generalize map1, map2, map3, and so on. The type signatures are clear. Now, applicative functors have all of these functions mapN. In fact, we will see in a later tutorial that once you have map1 and map2, it is sufficient in order to be able to define all the others. You don't need to have separate definitions for all the other maps. mapN, you can define mapN, taking a list of these, it's easy, once you have map1 and map2. We will not dwell on it in this tutorial. That's the subject of the next tutorial, because it requires us to consider the laws that must be satisfied by these mapN functions, and then it will be much easier to understand why all these functions are related to each other. But at the same time, it will require us to go much deeper into the relationships between these functions, the equations, and the laws. So that's going to be the subject of the next tutorial, part 2 of chapter 8. In this part 1, I'm just going to talk about practical considerations, practical examples of how you use this mapN, concentrating mostly on map2. mapN will be used in a very similar way. So what are examples where we want to use such things? Let's look at the example code. So the first example is the either type. So imagine we're doing some computations where results could be given as values of type A, or as you could have a failure, an error message that is represented by a string. An example of such a computation would be the safe divide function, where I divide, but I check whether it is not 0, and if it's 0, then I don't divide, I give an error. Now, this is just an example of this kind of approach, where your computations have the type op of double instead of double, and this is a type constructor that encapsulates some effect, some error accumulation or some other effect. So in this case, this constructor represents errors usually, as we have seen before. So let's implement map2 in a way that would help us understand how we can collect all errors. So map2 needs to have this type signature. It takes op of A, op of B. It also takes a function from A, B to Z, and it returns op of Z. So it needs to have type parameters A, B, and Z. How do we compute this op of Z? Well, let's find out. We have op of A and op of B. Now, op is an either, so we can match on it. Let's match right away on both A and B. Now, there's a case when we have two errors. And in this case, it would be interesting for us to accumulate these error messages. So let's not throw away information here, and let's do this. So we concatenate the strings. In more general situation, this type, instead of string, it could be some other type, which could be a monoid, and then we could combine the two values of a monoid into a larger value. In case we have one error and one result, we can't really do much except return that error. And in case we have two results, we can actually perform a computation that is requested, which is this function f, and return a write. So in these two cases, there isn't enough data to call f, because we only have one value but not the other. So we cannot call f, and the only thing we can return is an error. So this is how we implement map2. Now notice that this map2 does more than a monadic functor block would do, because the monadic functor block would stop after the first error. This one doesn't stop after the first error. It takes also looks at the second computation, and if it also is an error, then it accumulates the errors into this value. This is something a monadic functor block cannot do. It cannot accumulate errors, because once it finds the first error, it stops and returns that error. So here's an example how we could compute. For example, here's map2. I'm just going to apply this function to the values defined like this as an example. Now, in a real computation, this doesn't seem to be very convenient to always have to write computations like this. Scala can give you a lot of convenience by defining a domain-specific language with syntax and operators so that you don't have to write all that stuff. But under the hood, it must do this stuff. So this is the way it works under the hood for any kind of library that would do this more conveniently. So you could call this function map2 on two computations. Now notice they're both dividing by 0. So these two computations will give you two error messages. And now the function that you pass is a subtraction. That function by itself doesn't give any errors, but it never gets called because you actually have errors in both of these two computations. So the test asserts that we actually have two error messages telling you what you're dividing by 0. Now, if you instead wrote this kind of thing, which has the same type signature, then you would have just one error message. The first one would have stopped the functor block from continuing. So this is how it works. Now we can define map3. Let's take a look. It's a very simple type. Can't be so bad. Now, however, we now have 3 computations. Each could be an error or a result. So there are 8 possible cases. We're not going to write them down. That would be really not great. So how do we do that? Well, let's think about how we could use map2 instead of writing this function map3 from scratch. Map2 only works by applying it to 2 containers. Okay, let's do that. Let's apply it to A and B. And while the function f requires 3 arguments, we can't apply it. Let's not apply it. Let's just apply it to some function that doesn't do anything to the arguments, just accumulates them in a tuple, which is almost an identity function. Just to remind you that in the Scala syntax, this is not actually a tuple. This is an anonymous function that takes 2 arguments. And if you wanted a tuple, you would have to write like this, which is the tuple of xy going to a tuple of xy. This is the actual identity function on tuples, but this is not what we defined, so it's almost an identity function up to some syntax. We could have defined this syntax so that it is really identity. So we just combine these two. What's the result? The result is this. So it's an op of a tuple. Now we can use again map2 to combine this op of a tuple with C. And then the map2 will have this type of argument. Now we can apply F. So this kind of thing is how you could use map2 to define map3. Now clearly this can be generalized, a little awkward to generalize, but it can be generalized. The awkwardness comes from here. It would be hard to generalize this case expression. Obviously, if you have mapN, you need to apply map2, then again map2, again map2. When you do that, every time you have more and more tuples in your case expression, so that's a little awkward. Can be done with some more work, but I'm not going to look at this right now. There are easier ways of defining all these mapN functions. Here's an example of how it works. A map3 working on 3 computations of this type accumulates the 2 errors that you see. This third computation does not give an error, so that's fine. Now, a use case for this kind of type is where you want to validate values. So imagine if you have some case class with a few values, you want to validate them, and each validation is separate from other validations, just like each of these computations is separate. So only when all of the 3 parts of a tuple or a case class pass validation, you want to create actually a value of the case class. Otherwise, you want to fail. But when you fail, you want to gather all the errors. This is how you would do that. You would say, you do a map3 of these 3 validated computations, safe divide, and then you would apply that map3 on that to a function that takes 3 values and makes a C case class value out of them, which is c.apply. Now c.apply is a function that takes 3 arguments and returns a case class made out of them. So this c.apply is defined automatically by Scala. Very convenient. So in this case, in this example, obviously there aren't any divisions by 0, and so we get the result. The second, so we have gone through these 2 examples. The third example is when we perform future computations concurrently. And here's how we would do that. We would define map2 for futures. Now, since these arguments are eagerly evaluated, they're already given when you call map2, these futures already were started on some threads. And so we can just write the for yield block like we did before. These futures are not really sequential because they already have started. So they run most likely on separate parallel threads already when we are starting to evaluate this function. So that's why it's okay to define map2 through Flatmap for futures. Now that is a test. When we do a map2 like this on these 2 futures, and then there's another addition, so that's 1 plus 2, 3 plus 4, that would be 10. And mapN can be defined like this, so there's a list of futures and you return the future of a list. Well, that's not really a mapN. There must be still a function, so let's call it something else. In the standard library, it's called future.sequence. Sequence is a kind of confusing name. It refers to changing of the order of these two type constructors. First you had a list of futures, and then you had a future of a list. Very important and useful function in the standard library that essentially implements most of mapN. You still need to map this list to some other values. So the real mapN would take a list of futures. It also will take a function from a list of A to some B. So we need a type parameter B, and we will return a future of B. And the reason, and then we would just do that in order to get it working. So that was the example with the futures. Another example where applicative functors could be useful is when you have a reader monad or functions with some standard arguments, and you are getting tired of passing these arguments over and over to all kinds of functions. So as we have seen in the previous chapter, the reader monad does that kind of thing, and it turns out that the reader monad, whose effect is this constant value e that you could always read, which is kind of a standard argument of all computations that you're doing. Now this e is a constant, it is an immutable given value, and that's the only effect of this monad. So this monad always has independent and commutative effects. So in this monad, you don't have to worry about the order of effects. It is already independent. And in other words, we can define map2 via Flatmap. There's no penalty for doing so. Here's an example. Imagine we have some application that needs to use a logger. Now, a logger, we will just do a quick and dirty logger, which has a side effect, which takes whatever value of any type and prints it in some way and returns unit. Now, this is a very dirty way of doing logging, but it's quick. It's dirty in the sense that it's hard to see that you have logged anything or not, because this function doesn't return any useful values. But let's continue with that for now. A functional logger that is clean is the writer monad. It tells you explicitly that there is an extra value being created with each computation, which is perhaps a log message. And it tells you also that you combine the log messages together using a monoid. So that's a clean way of logging. But let's, just for the sake of this example, consider this logger. So we have an empty logger and maybe some non-empty loggers. And now suppose that every computation we want is going to be logged. So every computation is going to use this logger and call this print function many times for whatever reason. And so every computation needs a logger as an argument, because that logger will provide the printing functionality. And if you do that, also it becomes much easier to test such code, because then you can pass an empty logger, or you can pass a test only debugging logger, or anything like that. But then, of course, all your computations become more cumbersome, because now you have functions that have this argument. So here's, for example, a computation that adds two integers. It returns a logged integer. It is a function that takes a logger. It does this computation, logs it, and returns a result. So it's a typical kind of code that you would use. Now, suppose I wanted to combine these computations. So I'm logging 1 plus 2, I'm logging 10 plus 20, the results are x and y, and then I have x plus y. Now, changing the order of computations gives the same result, except for the side effect of printing, of course, because that is not going to be commutative. First it's going to print this, and then it's going to print that. But the side effect is invisible in the types of these expressions, and so the expressions are going to be equal after interchanging the order, as this test shows. And this is another illustration of the bad nature of side effects. You don't see them. You have no assurance that the side effects have been performed in the order you want. So for this example, it will be okay. So now let's define map2. We just define it via Flatmap, like this. Or we can define it by hand, like this, which is kind of obvious, because this is a function from logger to a, this is a function from logger to b, and this is a function from logger to z. So we obviously just call these two functions with a and b, provided by those two functions. So we call f on this. That's the only way to implement map2. Now, this way is exactly the same, actually. We can verify this symbolically, that the code is exactly the same. Because map is this for the reader monad, flat map is that. There's no freedom here. The types fix the code uniquely. And then we can calculate what is map2 of AB, which is going to be this, because this is the translation of the for yield construction. And we can do that by first looking at the map, substituting the definition of the map right here, and applying the function to the argument. So then you get this function, and finally we need to put that function into Flatmap, substitute the definition of Flatmap, which is this, and we get this code. So by just symbolically transforming the code, I step by step arrive at the code of the other function. So in this way, you could use map2, mapN, and so on, and have your standard arguments passed to functions. But why do that with the reader monad if you can just do the for yield construction? Well, what if you can't? There's not a monad somewhere. In case your type is more complicated than this, you might be in a situation where you don't have a monad, but still you need to pass standard arguments, and you can do that with mapN. Another example is the list, which is a monad. And we have seen that every monad is already an applicative because you can always define map2 via Flatmap. But there might be a different definition of map2. In the case of list, there are various definitions. We'll just use a standard one right now and show how you can transpose a matrix. So let's define map2 first of all. Well, map2 is a very simple thing for lists. It's a zip. So first we can zip. You see, what we need is a function from list A and list B to a list of pairs AB, and then we could just map with F. And that's what we write here. So we do an A zip B, which gives us a list of pairs AB, and we can map that. Now, the zip function has a specific implementation. We could change that, especially when A and B do not have the same length. Then there are lots of choices about what to do. You know, do you want to cut short, or do you want to fill with some default values or something like that? But let's not discuss it right now. We will see in the second part of this tutorial how to define map2 in various ways, in case that there are several definitions. So for now, we just use the standard library in Scala to have the zip function. So that's clearly what map2 does. So you can see that map2 has a close connection to the zip function for lists that takes two lists and returns a list of pairs. And then you just map over that list with a function f. So map2 on a pair of these two lists with a plus function will give you pairwise sums. So how do we transpose a matrix? Now, a matrix represented here as a list of lists needs to be transposed. So, in fact, we need to understand how we represent a matrix as list of lists. So let me have an example. So for this matrix is a list of 3 lists, and the transposed matrix is a list of 2 lists, where the first has these 3 elements together, and the second list has these 3 elements together. So to transpose them, what we need is to take the heads of each list and put these heads into a list of their own, and then we can use transpose on the tails of each list in the same way. So we're going to have a recursive function, obviously. So how do we do that? So suppose that this list of lists has heads and tails. So what does it mean, heads? So this is the heads. Now actually, what you want is to append this to this and to this. You want to have a list that goes like that. So clearly the head of that list is going to be the head of this. And let's transpose the tails. So the tails are these. So sorry, tails are these. If we transpose them, then we will have a list of these two. and then a list of these two. Now what we need to do is we need to append this to that list and this to that list. Now this append looks like a component-wise operation on this list and on the list of those. So that's where we use map2. We use map2 on heads, which is this, and on transposed tails, which is the transposed this, to append the first element to the rest, which means that we will append this to that, we'll append this to that, and so on. So it remains to transpose the tails. Now it's very easy to transpose the tails. We just call transpose on the tails right here. Everything else in this code is bookkeeping that is designed carefully to avoid problems where you have empty lists. Now that code is kind of cumbersome and error prone. You do a map with a function that returns empty lists, and here you just return an empty list. It took me a few tries to get it right. This code and this code. But the other thing is more important. So this is how we use map2 in order to concatenate component-wise this with this, at the same time this with this, and so on. So this is the kind of typical computation that applicative functors do. They do component-wise computations. Component-wise computations are independent of each other's results. So this is independent of this. And that's where you use applicative functors. And some tests to show that this is correct. So after these examples, in principle, there are a few other examples where you use applicative functors. And before going to those examples that are a little more complicated, I'd like to talk about applicative contrafunctors and applicative profunctors. Now, the reason I'm talking about this is that actually they are sometimes quite useful. You can have an applicative instance or a function such as map2 or zip for a type constructor that is not a functor. We have seen in a previous tutorial that type constructors could fail to be functors in a number of ways. One of them is when they are contrafunctors, that is, contravariant type constructors. But there's another way where they can be neither functors nor contrafunctors. And that happens when your type parameter is both in a covariant and in a contravariant position in the type constructor. So this is an example. So if you have A as your main type parameter, Z, let's say, is a constant type, A is your main type parameter, then this A is to the right of the function arrow, and this A is to the left of the function arrow. So this A and this A are in a covariant position, and this is in a contravariant position. Because this type constructor contains both covariant and contravariant position for A, it cannot be a functor and it cannot be a contrafunctor in terms of A. But nevertheless, it has still properties that are quite nice. It is called a profunctor when you can see all type parameters either in a covariant or in a contravariant position. I will talk about profunctors later in more detail. But for now, just keep in mind that it's very easy to see which position is covariant and which is contravariant. Just look at the function arrows in your type, and everything to the left of a function arrow becomes contravariant. If there is an arrow inside that, then it can again become covariant. So we have seen examples of this. So here's how profunctors can become useful. This is an example where we can define a semigroup type class instance for a type that has parts such as a tuple or a case class, where each part also has a semigroup type class instance. And let's see how that works. Just for brevity, I will define semigroup here like this. It's a very simple type class. It just has one method. And this method basically is equivalent to this data type. The product of two s's going to one s. So clearly, this data type, considered as a data type, is not a functor and not a contrafunctor in the type parameter s. Now, we usually don't consider type class traits as containers, as data types. But we could. And what will happen if we do is we will notice that usually they would not be functors and not be contrafunctors because they have too many things in both covariant and contravariant positions. So these two are contravariant position. This is a covariant position. But it has a profunctor because it has nothing but things in covariant and contravariant positions. In that case, it's going to be a profunctor. In fact, all exponential polynomial types are going to be profunctors. There's no way you could fail to be a profunctor as long as you stay within exponential polynomial types. Now, the interesting thing is that we could define a zip function for this type constructor. So let's forget for the moment that we're going to be using this type constructor just to define a few implicit values for the type class. And let's just consider that as a type constructor and try to see what the zip function would be for that type constructor. Well, a zip function would have this signature. We'll take one semigroup, another semigroup, and we'll return a semigroup of a pair. How do we define that? Well, it's pretty straightforward. You need to define the combine function that combines AB and AB into AB. Well, you just combine this A with this A into this one, and you combine this B with this B into this one, using the combine operation from the semigroups P and Q. And that's the code. And now we can use that to define a semigrouped type class instance for a pair. And it's just same thing. I'm just going to use this syntax, and to test that this works, I define semigroup instances for integer and double in some way, and I have a pair of int double, and now I'm able to use this syntax. So after this implicit definition, I'm able to use this syntax. So this is now a zip function is very closely related to map2. We did not actually use map2, right now. But once you have a zip, then you get your container of pairs, and all you need to do is to map your function of 2 arguments over this container to get map2. So zip and map2 are very closely related. Once you implement one, you can implement the other. And the second example I'd like to give is that let's consider this profunctor, and let's just implement map2 for it. Now, map2 for a profunctor has a different type signature than map2 for a functor. It's called imap2 in the cats library in any case, to indicate that this is not a functor map2. They call it invariant, so profunctors are called invariant, which is quite confusing to me because invariant has so many other meanings in different contexts, such as you make a transformation but something doesn't change. Then you say this something is invariant with respect to the transformation. But none of that is happening here. Nothing is being transformed such that it remains invariant. In geometry, for example, the length of a line segment is invariant under rotations. The area of a triangle is invariant under rotations. So that's the kind of context that I'm familiar with, and calling this invariant would lead me to ask, what is a transformation that you're applying such that this does not change? And that makes no sense at all in this context. Or for instance, in the computer science, there is something called loop invariant, which is an expression that remains constant throughout each iteration, between each iterations of the loop. There is no loop here, and nothing remains constant. So again, that meaning of the word invariant does not apply. So that's confusing to me. So I don't want to talk about invariant functors. I want to say profunctors. That's shorter anyway. So let's look at how we can implement an analog of map2 function for this type constructor. Now this type constructor, as I said already, it's not a functor. It cannot be possibly a functor because it has the type parameter a in a contravariant position and also in the covariant position, so it cannot be a contrafunctor either. But it is nevertheless what I call zippable. You could define zip for it, and you can define imap2 for it. Let us see how. How do we define imap2 for it? So here I define this type constructor f. Now, in order to do a map2, we use the function from AB to C, and we applied that to a container with A and container with B. So here we have a container with A, here we have a container with B, and here we have a function from AB to C. But it turns out that's insufficient. You also need a function from C back to AB. Only then it makes sense to define mapping functions for a profunctor. And the reason is that when you want to define a mapping function, then you transform the type parameter, say A, into some other type parameter, say C. But when you have your type in a covariant position, then you just compose with the function that transforms. When you have your type in a contravariant position, you have to have a function that goes backwards from C to A, say. And then you would take a C you would use that function to get an a, and then you put that a as an argument in the contravariant position. So for this reason, the profunctor requires a function from C back to AB. Now, if this were purely a contrafunctor, then we would just use this function from C to AB, and we will be done. I remind you that contrafunctors are just very similar to functors, except the map function takes the opposite direction of transformation in types. But here it is neither a functor nor a contrafunctor, and actually we need both functions, f and g. F goes from AB to C, and g goes from C back to AB. And then it turns out we can do what we need. How do we do that? Well, so let's write the code being guided by types and by the intuition of what we need to do. So we need to produce an f of C and Z. So that's going to be a function from ZC to CC. So we need to return a tuple of CC. How do we do that? Well, it's obvious that we need to use these functions f and g somehow. We have a C. If we use g on it, we get a pair of a, b. Let's do that. So we get some new a and new b by back transforming C. So now these new a and new b need to be substituted into the contravariant positions, which are these positions. So we take faz and we substitute z and a. Now z, there's only one z, and that's not going to change because we're not transforming the type parameter z at all. So z stays the same, but here we substitute new a and new b into the contravariant position of the f. The result is going to be pairs of AA and BB. So let's call them new AA and new BB. So now we can apply f to this data to get a new value of C. We need to have two different values of C, and it makes sense that we would use the first two and the second two like that, to substitute that into f. So that's how we would do that. Let me try to improvise and define a zip function for this type constructor. So what would be a zip function? So it will be faz of type f of az will be fbz of type f of bz, and the result will be f of pair AB and Z. Now the Z is not going to change, we're just going to transform A and B. Now what do I need? I need type parameters A, B, and Z. So how am I going to do that? Well, obviously f is this, so I need to have a function that takes Z and a pair of AB. Now, in Scala, I cannot just have a function that takes that as arguments. I need to do a case expression so that I destructure these arguments, as it's called, or a match on them. So now I need to produce a pair of actually AB, AB. I need to return a pair of tuples like that. what I have is a functions from ZA to AA and from ZB to BB. So clearly, I need to use those functions. If I apply FAZ to Z and A here, I get an AA. And it makes sense that I'll put these A's here, A and A. And I'll do the same with B. So let me write it down. New AA is FAZ of ZA. New BB is FBZ of ZB. So now I've got my pairs, BB and AA, and now I can return this, which is going to be basically this. I'm going to return this pair, and I'm going to return that pair. Now, if you compare these, and the code appears to be quite similar, except that I don't have an F, and I don't have a G. And that's quite typical of these pairs of functions. One of them is equal to the other when we put identities instead of types, instead of some arguments. And the other is obtained using some kind of Fmap. So we've seen this pattern before, and that's what it will be. But that will be in the next part of this tutorial. So in this way, we find that this kind of type constructor has a zip-like function, which has exactly the same type signature as a typical zip would be. I mean, this, if you ignore the extra type parameter, then it will be just a typical zip, f of A, f of B, going to f of pair AB. Just like lists instead of f. However, this f is not a functor, it's a much more difficult object, perhaps, to work with. So that was the example I was interested in showing, how you can define zip and IMAP2 for those profunctors. Now, I call them non-disjunctive, and the reason is these type expressions do not contain any disjunctions. And actually, if they do contain disjunctions, then it's not always possible to define zip. So I call them zippable. So not all of them are zippable. So it's just a lot of them are, but not all. But when they do not contain any disjunctions, then they're always zippable. So with this understood, let us now consider an interesting practical case where we can use this knowledge and actually make code simpler. And this case is the so-called fusion for fold. And the idea is that fold is a computation that iterates typically over a container. And if you need to iterate several times and then do a computation on the results, that's kind of wasteful. That's better to iterate once and accumulate more intermediate results. But when you write code for this, it becomes cumbersome. You have to do it every time. You have to write a different complicated fold function. So the idea here is that we can actually automatically merge several of these fold functions into one so that everything is computed in one traversal. So there are several libraries. So one library is called ScalaFold, which is this one, where this is implemented, where you can combine different folds. So as an example, I will show you if you want to compute the average of a list, then you would have to traverse the list twice, once to find its length, and another time to make a summation. And that's wasteful. And so you can merge these folds into one. So you can define a fold separately and then merge several folds into one and apply that one fold to a list traversing just once. So let's see how that works. So fold is an operation that takes several parameters. So let's remind ourselves. For instance, list 10 would be our running example of data. So fold left, for instance, what does it require? Requires an initial value of some type B and an operation that takes the previous accumulated value, a new element of the list, which is going to be of type double, and returns a new accumulated value. So a fold essentially takes these two values, when you apply that to the list. So let's just have a type that encapsulates these two arguments of a fold left. So this is going to be a very simple type, just going to be a tuple of these two values. So let me get rid of this. Just like that. So Z is the type of values in your collection, and R is the type of the result. So in order to call the fold left, you need to provide this data and the list, of course. So let's put this data into a type constructor of its own. So here I called it fold 0. So it's kind of a version 0 of this implementation. I put it into a case class. So this case class is a product, and I just put names on it for convenience. A very simple syntax extension will make it possible for us to apply this fold value to a collection that is foldable. Now, the foldable type class we haven't looked at yet, but basically just it's a collection that has fold left. Basically, all polynomial type constructors are foldable and no others. So I prefer to think of foldable as just a property of polynomial type constructors. Now, it's interesting that we can define an instance of what Cat's library calls invariant semigroupal, and what I just called in the previous code snippet a zippable profunctor. Neither of these names are particularly nice. As I said, invariant just gives me all kinds of wrong associations, and semigroupal is a difficult thing to do, a difficult thing to understand because it is not a semigroup. So semigroupal suggests that it is a semigroup, but it isn't. So zippable profunctor is the same as invariant semigroupal. I'm not sure what terminology is better. Neither is standard. Neither terminology is widely used right now. So let's look at this. Obviously, we have R in the contravariant position, and also we have R in the covariant position. So again, this is going to be a profunctor, not a functor. No matter, we can do a zip on it. And I just use my Curry-Howard library to implement the IMAP and the product methods. Now the product is the same as zip, just the CATS library uses the name product instead of zip. IMAP is this profunctor property where you can map fold 0 of ZA to fold 0 of ZB if you have functions from A to B and from B to A. So this is a typical thing that a profunctor requires. You cannot map a profunctor of A into a profunctor of B unless you have functions that map in both directions. Because you would use this function to substitute in the covariant positions, and you would use this function to substitute in the contravariant positions. And since you have both positions for your type parameter, you need both functions. But luckily enough, this type is sufficiently straightforward so that my Curry-Howard library can automatically implement these methods. And then I can implement zip as a syntax by just using this product, because zip is exactly the same type signature as this product in the CATS library. And now, how will we use that? So let's define some actual folding operations for numeric data. For instance, the length of a list or a sum of elements. So the length is going to be a fold with initial value 0 and updater that just adds 1 to the accumulated value, ignoring the value that is in the collection. And here I've used the numeric type class, which comes from the Spires library. Let me see what was so ridiculous. Oh yeah, here's the Spire Math library. So I'm using the Spire Math numeric because I found that standard Scala's numeric very hard to use. And Spire is a good library that has lots of interesting types, and I could recommend using that. So for numeric n, we have operations such as plus, minus, and divide, and multiply, and so on. So for those, it makes sense to do a sum by folding with this update function that accumulates the sum, starting from 0. Now, we can combine these two. Now, these two must be defs rather than vals, because they have type constraints, type class constraints. So type class constraint is really an implicit argument of a function. So it must be a function, it's not a value. And it has a type parameter, so it cannot be a value anyway. It can't be a val in Scala if it has a type parameter and if it has an argument, type class constraint. But it doesn't really matter. We can just do it like that. Now, if we apply the zip operation, and we get a fold that accumulates a pair of two numbers. So it accumulates the length and the sum separately. So we can apply this fold to a list. We get this pair. And then we can divide the sum by the length and get the average of the sequence. Now, so in this way, we already realized what we wanted. We have combined folds, and this is a single traversal, because this is a single fold left operation. Now this is, however, inconvenient because we need to do this combining, and then we have a tuple, and we have to take parts of this tuple. We would like to incorporate this final computation somehow already into the fold, so that when we apply this, then all of this is done automatically. And also, we don't want to worry about this so much. We want things to be automatic. How do we do that? Well, so the idea is that this final computation that takes the accumulated value, does something to it, and gives you a different result, perhaps of a different type. Like here, the type of the accumulated value was tuple n, and the type of the result was just n. We would like to put this final computation also into the data structure, that is the fold, so that when we apply the fold to a list, all of this is done automatically. Well, easy to do. We define this fold 1, which is the same as before. It has initial value, it has an updater, and then it has this final transform, which takes the accumulated value and returns some result value. And the types now are Z, A, and R. So now we have 3 type parameters in this data structure, but so what? We can have as many as we need. Define a syntax, so I do this fold L1. Now, unfortunately, the syntax cannot clash with other defined syntax, so I need to do this fold L1. I cannot just do fold left. That would clash with Scala's standard fold left. And in order to apply this new comprehensive fold, so to speak, first we need to apply an ordinary fold to the initial value and the updater, and the result of that needs to be transformed using the transform. So that is how we apply the fold. There is still just one traversal, because there is just one call to actual fold. This is the fold left. The foldable class has this fold L function. So there's only one traversal. And we like to keep it that way, so there won't be any, even if we combine many folds together, there will only just be one traversal. So how do we combine the folds? Well, we do the zip, and I just told it to implement. Nice. Now the interesting thing that happened after we added this transform element to the case class is that now the type parameter R is only in the covariant position. It's only in the covariant position. The A, of course, it is a contravariant position here, but R is only in the covariant position, which means that with respect to the parameter R, this type constructor is a functor. So if we use fixed values of other type parameters and only vary the type parameter R, with respect to that, it is a functor. So we just implement automatically how the functor instance. And now, how did that happen? Why is it a functor? Well, strictly speaking, formally speaking, it's because the type parameter R only occurs in the covariant position here. But actually, the implementation of map for this functor is very easy. You want to transform R to some t, just modify this element. compose this function with the function from R to T, and you get a function from A to T. And that's it. So basically, the map operation is the same as and then applied to the transform element of the tuple, or part of the case class. So that's why I did not write code here, I just said implement, it works. It is completely fixed by types. Now, defining the length and the sum operations as folds, now we have these type parameters, which I wrote down because you have to. Not on the right hand side, but you need to write them on the left hand side. It's a function definition. So now you see same thing, except I put identity here because it's a transform, which is identity. I need to put it in. Let's combine the sum and the length like this. So we do a sum zip len. So that's going to be accumulator of this type. And then we apply this function, which will divide the sum by the length and get the average. So the test works. Now, actually, this is still quite cumbersome to write this kind of thing. Why can't we write just this? We can. We just define syntax instead of writing this. Syntax that would allow us to write that. So here's the syntax. As a syntax extension, we define all these operations. An arbitrary binary operation basically does this. Just an x zip y, exactly like what we did here. And then a function. And this is the binary operation. So in this way, we can easily define all the binary operations that we want. And here's the code now. Very easy to write. The double type parameters, unfortunately, are required. Or you could put the type parameters here, but that would be less intuitive. So this is the way that we can combine folds in a single traversal. Note that the same structure is required for scan. So scan is like fold, except all the intermediate accumulated values are still kept in the sequence or in the container. And so that's how you would apply a fold operation that we defined as a scan. It is very easy because scan left has exactly the same types of arguments. And these two arguments are what the fold structure gives, and then you just need to map with transform. Now, unfortunately, this is going to be twice the traversal that we had. Because we do a scan left, that's going to create one sequence, and then we do a map. It's going to be a second traversal. There might be a way of avoiding it, but that's less important. That's certainly just two traversals. We can combine as many folds as we want in a complicated way. There's still going to be just two traversals. So if we can somehow refactor this to have just one traversal, maybe by refactoring the scan left itself, that would solve that problem. That's not the focus of this tutorial. So here's an example. So if we use the average and do the scan instead of fold, then you have all the intermediate averages accumulated as you iterate over the list. So finally, I would like to point out the difference between applicative and monadic functors. So we have seen that fold could be seen as a not functor, as a profunctor, and yet it has a zippable property, and so you can merge these folds into one. Now this merging is similar to component-wise operations. So for example, average of a sequence is a division of sum of a sequence and the length of a sequence, and sum and length are completely independent of each other. So that's a component-wise operation in a sense, and so that's applicative by our intuition. Now, monadic operation, on the other hand, would be such that we depend on the previous results in order to compute the next iteration of the fold. And so, for example, we could compute a running average that depends on running average that we just computed previously. So we can combine folds together, but each new iteration would depend on the previous accumulated result. So that would be a monadic fold. So let's see how that works. We are going to continue to use this type constructor because it's a functor in R, and as we know, a monad cannot be not a functor, could not be contravariant or profunctor. It must be a functor. So if we want a monad so that there's a useful kind of flat map, then you need to use this. We cannot use fold 0. That was not fold 2, fold 0. All right, but actually it is more difficult than that, because when you combine two different folds, the type of the value that you accumulate must change. It must be a tuple of values that you previously accumulated. So let's look at the type signature of the combine. So you see, you combine. I skipped over this, but if you look carefully, the first fold takes values of type Z from the sequence, accumulates values of type A, and returns results of type a result of type R. The second fold has a different accumulating type, and so the final combined fold needs to accumulate a pair of AB, and it returns a pair of RT. And so this is not quite the same as the type signature of a usual zip, because not only this type parameter is modified, but also this one. But this is necessary. So it is a slight generalization of zippable or zip or type signature, but this small generalization is important and necessary. And similarly for the flat map, if we want to define flat map, we would have to change the type of the accumulated value A. So here's what it would be. If you want to do a flat map for fold, then it will take two arguments. One will be some initial fold. Then you take the result of that fold, and the function will compute some other fold using that result. And then you want somehow to combine these two into a fold that returns T. But this fold certainly needs to accumulate A as well. Otherwise, you won't be able to get R's that are necessary for this one to work. So the resulting fold must accumulate a pair of AB. There's no way around that. So this is going to be, again, a slightly generalized type signature for flat map, where usually you would not see these type constructors would be absent, and you would just have f of r to f of t, returning f of t. But now you have to return this kind of thing. And that is, as I just explained, unavoidable. So how do we do that? Well, we basically very carefully look at what is going to be computed when we apply this combined fold. So first of all, what is going to be the initial value of this type? Well, the initial value needs to be of this type. Well, clearly, we need to use the initial value of the first fold. And where would we get the initial value of the second type? The only way to get it is when we apply f to something. But to what? We need some r. Well, the only way to get r is when you transform with the first fold from some a. And there's only one a here, which is this initial value. So f of this is the new fold that has initial value b. So let's take that and put that into the tuple. Let's now look at the update. How would the update work? Now, the update needs to be of this type. Clearly, the only way for us to get a new value of a is to use the update from the first fold. So let's call it new a. Now, the only way to get anything of type b is to go through this function f. So we need to apply f to something. To what? Well, clearly to some r, and the only way to get an r is to transform with the first fold. And the only reasonably correct thing to transform is a new a. Well, we could transform the old a, but then this is not right because we want the second fold to depend on the result computed by the first. But this is debatable. We could have a situation when this could be a1 here. It just seems to me that this is better to use an updated value. And in a specific application, you want to see if this is so. So this is a new fold. So this is a new value of this type. Now what we need is a new b. So we need to update. Obviously, this b, we need to update with the new fold. We get a new b. So now this is a new a and new b that we accumulate. So that's how the updater works. There's just one place here where we have some ambiguity, some choice. Everything else is pretty much fixed. The new transform is going to be from AB to T. And that's, again, pretty easy to understand that we have to get a new fold somehow. And the only way to get it is to do this. And then we transform with B1. And we get a T. And so then we return a fold that has this init, this update, and this transform. So let's see how this fold works. Let's have the running average of running average. So one way of doing this would be to do double traversal, which is actually quadruple traversal, since each scan is 2 traversals, but let's ignore this for now. So it's a double traversal. So first average gives you this, and then when you again do running average of this, another scan, with the same fold, then you get this. Now let's combine the two averages together in a monadic way. So how would that work? We do the average one, we do a flat map. So X is this running average after transformation. So it's a running average. And for each running average, we return a fold that accumulates that running average. It does not actually accumulate values of Z from the initial sequence. It accumulates this running average for each fold. And then we divide that by length. So see, this is how we would write that. And now a single scan gives us exactly the same results. So in this way, we have combined two folds into one in a monadic way. We can use the for yield syntax, the functor block, which is easier to read. And it would look like this. So X is the running average from that. Accumulator is the result of this accumulation, which depends on X, which accumulates the values of X. It actually ignores the Z. It accumulates the values of X. N is the running average or running value of this fold. So these variables are to be visualized as running values of a fold. And finally, we divide this accumulator by n. Very visual. And we have again the same result. So I would like to emphasize the difference between applicative fold combination and monadic fold combination is that applicative folds cannot depend on each other's intermediate results, but monadic fold combinations can. That is the main intuition behind understanding the difference between monads and applicative functors. Applicative functors express computations that are independent of each other. They're kind of component-wise computations, but monadic combinations describe computations that are possibly dependent on each other's running values. So the previous value can influence what you get in the next value. Now, there's a library called Origami that gives you a monadic fold, but they're actually not monadic. They're monad-valued folds. If you take a look at that, you would see it says monadic folds, but actually they're not the same as what I just described. They must operate on a monad, and their update has this type, which means that your updater includes a monad as a result, and every iteration of your fold must flat map over this monad. So that's why I would call this a monad valued fold. So the result of the fold is a monad value. And so every time you accumulate your result, you update it, you actually have to evaluate a flat map on that monad. So that's a very different thing, which is useful in different ways. It is not the same as the monadic composition of folds. So take a look at these libraries in more detail if you're interested. And the final worked example that I'd like to explain is the difference between applicative parsers and monadic parsers. So again, this is really a difference between how you compose these parsers together. Just like with folds, how you compose folds together. You can compose them in an applicative way, so when they don't depend on each other, but you must compose them in a monadic way when they do. So the same thing happens with parsers, as I will show now. Parsing is a very big topic with a lot of different algorithms and complicated grammars that you can parse in different ways. And I'm going to explain very basic things that you can do easily while trying to do this on your own. You will certainly run into trouble, but that's because parsing is hard. Easy languages can be parsed easily. So that's why I take examples of very easy languages for parsing. So my first language for parsing looks like this. It's either a number, so this is end of file or end of string, either a number, or it's this HTML tag that I invented with a number inside and a close tag, or it's several of these tags and there's always one number inside. And the tags must be balanced. There must be only one number. And the idea is that you take a square root as many times as you put these tags. So you evaluate this to a number by taking square root as many times out of this number as you have the tags opened. And the tags must be balanced. So here's an error, for example. Not closed, not opened, open, closed, but then there's junk at the end, which is also not allowed. So those must be errors. Those must be signaled as errors. So here I just created a type for errors, which is just a list of strings. And these are the typical errors that I want to detect. That tags are closed, or not closed, not opened, or there's no number, and so on. So how do I even approach this situation? Well, it's a very simple idea, is that a parser is a function that takes a string and it tries to get something out of that string, and if it succeeds, it gives you a value that it computes, and it also returns the rest of the string that it did not consume. So it consumes some part of it and returns the rest of the string. Here's a type that could be used for very simple situations like this, where you take a string and you return a tuple, which is either of error and some result type, and also unconsumed remaining portion of the string. Now, if you failed to parse, then you return an error of some kind, and if you did not fail to parse, then you return the value that you found, computed in some way. And so this is the first idea, is that you will define the values of this type and you will combine them. And the language parser will be a combination of these smaller, simpler parsers. So here are the simpler parsers that I found necessary for this language. The first, the simplest parser is that it's the end of file. So this parser succeeds only when the string is empty. Then it returns unit. So it's a parser with unit type parameter. It returns unit, otherwise it returns an error. So I'm going to use that when I require that there should be nothing else anymore in the string. And the second parser I found necessary is the one that actually gives an error if there is no content in the string. So it kind of says there must be content in the string. Otherwise, it's not right. Then I have a parser for number. So I have a regular expression. I'm just using very basic tools. It's certainly not the best way to parse a large amount of data quickly, but I'm interested in the principles of how this works. So parser of int will take a string. It will match the regular expression on the string. So I'm using Scala regular expression standard library, which operates on string as if it's a case match, and each variable here, the pattern variable, will be equal to the group that is matched. So after this, if this is matched, then I have this number and I have the rest of the string. And I return this integer and the rest of the string. And if I did not match, then I say there's no number, and I return the entire string. I didn't consume anything. So in the same way, I define other parsers. So for example, open tag. If it's this, then I return that. Otherwise, I return errors. Close tag. All right, so these are my test strings. Now, how do I combine parsers? So this is the most important question. So the first combinator is a zip-like combinator, it's applicative combinator. So let's call it like that. And the idea is that I will combine two parsers, let's say parser A and parser B, I combine them, by letting first parser A parse something, then also letting parser B parse the remainder, and then I gather their errors together in an applicative fashion. So if they gave a result, great, I return a tuple. If they gave errors, then I collect all these errors. And if there are two errors from both of them, then I collect all the errors. Just like we did initially in the example with either, where we could define the applicative instance, or map2, by collecting errors rather than stopping at the first error. So that's the applicative combinator, or zip, of the two parsers. However, note that the second parser depends on the first, because the second parser runs on the rest that is remaining after the first parser has run. So there is a dependence of the second parser on the first. It's just that this dependence is not in the type A. It depends on the other things, on the context, on the string that is passed around invisibly. Invisibly, that is, to the types A and B. The type A doesn't know that there is a string being passed around. So from the point of view of types A and B, these are independent, but actually they're not independent. So the parser B is run after parser A has run. However, it is applicative nevertheless, because parser A failing does not make parser B necessarily fail. Parser B could succeed when parser A fails, and then, or parser B could also fail, and then both errors would be collected. So that's the difference. There's also a monadic-like combinator that uses Flatmap, where we first do parser A, then we discard its result, and then we do parser B. So if the parser A fails, then nothing will be done. So this will not collect errors from parser B. Another important combinator that has nothing to do with monads or applicatives is this alternative combinator, which is that parser A will be run, and if it succeeds, parser B will be run. But if parser A does not succeed, if parser A fails, parser B will be run. If parser A succeeds, parser B will not be run. And so parser B is actually here passed by lazy evaluation for reasons that I will explain shortly. So how do we do that? So first we run parser A, we get the result and the rest of the string. If the result is not empty, then we just return that. If it is an error, well, that error is ignored, and we try parser B. So that's the alternative. And then we define map and Flatmap, because parsers are functors. Let's check that is a functor. What is a parser type? Parser type is type parameter A is here to the right of the function arrow, so yes, it is a functor. Now, let's define the language. The language is defined like this. So first of all, it must be not empty. So, and this is the monadic combinator. So everything will fail if this fails. So if the string is empty, then everything fails right away. Nothing else is tried. If it's not empty, then we try to parse the number. If so, we map it to double. If it fails, then we try open tag, and then again we use a monadic combinator, because if that fails, then we should fail. It's either a number or an open tag. And it should not even try anything else. So what happens later is, again, we use language rec, so it's a recursive call. Open tag can contain any other thing in the language. It can again contain more open tags. So we do a recursive call and then close tag. Now this is an applicative combinator. So if this fails, we can still check that this fails or not. And the result is then mapped into square root, because we have here, if this succeeded, then we had a tag, which is a square root tag, so we have to compute a square root. So in this way, we define just the language of these tags, and then the final parser is this recursive language parser followed by end of file. And this is again an applicative combination, so we can detect junk even if this failed. Junk at the end of file will be detected. And then we map to the first value returned by this. So then it's a parser of double. Finally, we define the function parse language that takes a string and runs this language parser on the string and takes its value, which is going to be either of error or double. And here are the tests. It works. For example, parse language of this is 123. Parse language of this is 11, square root of this. Parse language of that is 10, and it's a square root of square root. These are not closed, so an error, junk at end. And here we actually find several errors. There's not opened, not closed, and here is not opened, not closed. So this, for example, we find that the tag is not opened, the tag is not closed, and there is a junk at the end. So obviously we are able to find all those errors at once. So as a second example of a language, consider this. A number surrounded by tags, but now the tags are arbitrary. Their tag names are arbitrary, they just have to be balanced. So there must be B and B, C and C. Now this is a different language where the parser depends on the result of the previous parse. Now here the parser did not depend on the result, because this is parsed independently of whether it is inside the square root or not. This by itself is parsed and gives you 100, regardless of where it is. It does not depend on that. But in this second language that I consider, that is not true, because this needs to be followed by C, which, so if this were C, that's an error. So you need to know that you have parsed B here in order to parse this correctly. So parsing this depends on parsing this. And that's why we need to use a monadic combinator. So I again define a few different small parsers and combine them into larger parser. So I find two parsers that parse any tag and return the tag name as the result, and then a parser that takes a specified tag that should be closed as an argument. So now this is a function that returns a parser, and I'm going to use a Flatmap so that it's a very similar parser as before. I have an end of file is error, then I parse a number, and then if not a number, then it's any tag, but the tag that I parsed needs to be closed right here. So in this way, I depend on the results of the previous parse. So this is when monadic combination is required. And here are the tests. So, and just to highlight the difference, so we do find several errors here as well, because we use applicative combinator here and here as well. But now we find fewer errors at once, because, for example, here, remember this incorrect input that was tested here. Here we got that it is not opened, not closed, and junk at end. Here we only see that it's not opened and junk at end. We do not see that this is not closed, because the closing tag monadically depends on the result of the opening tag, which failed, and so nothing was tried. So the parser, the little parser that was here, never got called. And so it never had a chance to fail and to tell us that a tag was not closed. So unfortunately, there's no other way to parse this language in this simple-minded approach, because we have to use this Flatmap. We have to depend on the result of this in order to check that this has the same name. So this is the difference between monadic and applicative functors. Applicative functors describe computations that, so to speak, they occur component by component independently. So there are several parts, and each part is processed independently, and the results are all accumulated. So mapN is a good example. So you have several parts. They're all processed independently, component by component, and the results are put into another container. Whereas monadic combination means that each next step here depends on the result of the previous step. And that is sometimes necessary. However, the parsers is an interesting example, because actually, as I just showed, parsers do depend on previous results, because the parser that is next gets the remaining string. And so it depends on how much of the input string was consumed by the previous parsers. And so for this reason, even if you only have applicative parser combinators, you still cannot say they're fully independent. And so, for instance, you wouldn't be able to parallelize the parsing. But in many cases, applicative combinations can be parallelized, as we showed in the example with the futures. So here are some exercises on this material. So here you should implement map2 or imap2 as appropriate for these type constructors. Some of them are not functors. And as I showed for the semigroup, but you should do the same for the monoid to define a type class instance for the pair. Then you should define a monoid instance for the type fs. Now this is S is not a type parameter, is a fixed monoid type, and so it's just applying a type constructor to a fixed type. I should show that this is a monoid. This was similar to what was done in the previous chapter for monads, but now for applicative, so you don't need f to be a monad for this. And some exercises for parser and folding combinators. This concludes part 1.